Welcome everybody to the third lecture in this series. My co-host Michael Wright is not able to make it today. He's attending a meeting in Dresden, so he sends his apologies. So today we are delighted to have Professor Albert Schwarz speaking. He has had an extraordinary career as a mathematical physicist. However, he prefers to call his area of research physical mathematics, this being mathematical ideas which are of current interest for their potential application to theoretical physics. Albert grew up and studied in the former Soviet Union and wrote his first research paper way back in 1952 at the age of 18. And in all, he wrote 7 papers in his undergraduate years. He completed his graduate school at Moscow University in 1960, working largely on problems in topology. Subsequently, he was a professor in the Department of Theoretical Physics at the Moscow Physical Engineering Institute during 1964 to 1989. During this period, he interacted with several influential Soviet mathematical physicists, including Berezin, Faddeev, and Sinai. In October 1989, Albert moved to the United States, and after spending a year at Princeton, Harvard, and MIT, he took up professorship at UC Davis, where he has been since. Albert has done distinguished work on very diverse topics, ranging from topological quantum field theories, supergravity, instantons, to non-commutative geometry and its applications in string theory and M theory. He has investigated deeply into the BFSS and IKKT matrix models in the context of M theory. Perhaps his best-known work is the one with Alan Cohn and Michael Douglas at the IHES on non-commutative geometry and matrix theory. I'm also very happy to note that he has collaborated with my distinguished Indian string theory colleague, Ashok Sen. Today, Albert will speak to us on Jordon algebras, quantum mechanics, and particle physics. Over to you, Albert. Very happy to have you with us.
Okay. So thank you for the introduction. And now I would like to talk about quantum theory, particle physics, and Jordon algebras in this order. So really, I will start with general questions, and then I will come to Jordon algebras. So I will talk, first of all, about geometric approach to quantum theory that I'm developing these days. So some words about other approaches. So everybody learned quantum mechanics from textbooks, where the basic notion is Hilbert space and observables as operators in Hilbert space. But this is not the best way to work in quantum mechanics, because you always can work in Hilbert space. The problem is that if you have the same model, you should use different Hilbert spaces. Much better ways to use algebraic approach to quantum theory, where the main notion is the notion of associative algebra with involution, that is called an algebra of observables. This is not quite precise terminology, because observables are only self-adjoint elements of this algebra. And was noticed already in searches of last century, right after beginning of quantum theory, that there is some discrepancy here. So we are using all operators, but in physics,
Albert, sorry, could you please unmute yourself?
so do I understand that you didn't hear me all the
Yes,
time?
yes, go ahead, please.
Did you hear me all the
Yes, we could hear you. There was a small glitch. Please go ahead.
Okay. But this approach using Jordon algebras didn't go very far in modern physics. Maybe it will reappear after this geometric approach, because there Jordon algebras arise very naturally. So I'm talking, what is the geometric approach to quantum theory? And the starting point is the set of states. That's definitely you should have in quantum mechanics. And it appears that using the starting point, you could develop the whole quantum theory. In particular, first of all, you can prove the coherence, starts from random environment. You can use the coherence to derive probabilities, formulas from probabilities. And this is derivation that doesn't require any axioms. This goes from first principles. Then, if you have time, and space shifts, you can introduce the notion of particle and quasi-particle. You can define scattering. You do not have usual scattering matrix, but you have something that I call inclusive scattering matrix. It can be expressed in terms generalized of green functions. And as I said, the relations of Jordon algebra to Jordon algebras appears very naturally. Please scroll. And what is also interesting, that the geometric approach allows us to go beyond quantum theory. So you can consider classical theory this restricted set of observables. You can assume that our devices can measure only some observables, and you can get usual quantum mechanics, and you can get theories that are should be considered something that goes beyond quantum mechanics. I will have not time probably to talk about this stuff, but I will be happy to talk about this in the second hour, answering the questions. Maybe I'll have some time to say something during the first hour. So please scroll. Now, I should say a couple of words about this geometric approach. So as I said, the beginning, from the very beginning, I should have a set that I call set of states and denote by curly C naught. And I should have a notion of mixture of states. The mixture of states is a very general notion. It appears everywhere, not only in physics, but also, say, in economics, where you have mixture of strategies. So I assume that the set of states contains also mixed states. And this means that the set of states should be considered as a convex set. The extreme points of this set are called pure states. And also another thing that I should consider, the cone of states, non-normalized states, denoted by C. And what I have in mind here, that I can consider non-normalized states that should be identified if they are in the same array. You can obtain one state from another state by multiplication by a number, and then you should say that these states are equivalent. Please scroll. Then what should I have? I have a set of states, and I should have some evolution of the states with time. Then I should, this evolution operators should map the set of states to itself. So I should have an automorphism of the set of states, but not necessarily I should consider all automorphisms. I should have some subgroup of the group of automorphisms that I denote by curly V. And the evolution operators are solutions to equations of motion. That is the most general evolution equation that you can invent. So you have basically the equation of motion in the form d sigma over dt is equal to h sigma, where h is some operator which describes evolution for infinitesimal time. It should belong to the Lie algebra of the group V. And we can say that that operator of evolution is an exponent of ht. But you can consider also the case when h depends on time, and then evolution operator is solution again defined. Again, is defined by these evolution equations of motion. The only difference is that you cannot write the solution in the form of exponent. So then I define the notion of observables. And the observable is a pair where you have this evolution, this infinitesimal evolution described by some operator A from daily algebra of the group V, and some functional that is invariant with respect to evolution. So I will show this stuff on examples on the next slides. Please scroll. First of all, I would like to say that you have classical mechanics, where you have this cone C described as a set of measures on some symplectic manifold. And these are non-normalized states. And normalized states are normalized measures when the measure of m is equal to 1. The observables are simply functions on symplectic manifold, and every such function can be considered as a Hamiltonian of some Hamiltonian flow. And this Hamiltonian flow belongs to, it defines a symplectic morphism, canonical transformation in physical language. And the V is the group of all canonical transformations. Please scroll. So now we can talk about quantum mechanics. In quantum mechanics, C naught consists of all density matrices. The operators, positive operators that have trace belong to the trace class. And if you do not have the condition on the trace is equal to 1, then you have non-normalized states, and normalized states, the density matrices, they should have trace equal to 1. And then you have this group V. It consists of unitary operators that act as conjugations on density matrices. And the equations of motion is the equation of motion for density matrix. This is simply this Hamiltonian quotation marks is simply commutator with some self-adjoint operator multiplied by imaginary unit. So I can say that every self-adjoint operator specifies a one-parameter family of unitary operators, and it also specifies a linear function. It's a standard expression of mean value of operator, trace A by K. The observable is a pair of self-adjoint operator and this linear function small a. Please scroll. There is another more general theory, this quantum theory in algebraic approach. Here the starting point is a unit of associative algebra with involution, so this it is called star algebra. And here C is the space of positive linear functionals. You impose the condition omega A star A is greater or equal to 0 is the condition of positivity. And the condition of normalization, if you consider C naught, this is the condition that omega of 1 is equal to 1. This generalization, standard approach to quantum mechanics, the unit of associative algebra is simply the algebra of all operators in Hilbert space. So then you define this group V is the group of involution preserving automorphisms of this algebra. And you can say that they act on algebra, but they act also on states. And again, you can identify, you can take self-adjoint elements of this algebra. And it specifies one parameter group of automorphisms of A. This group acts also on states. And you have also functional on the set of states. So again, you can consider observables. As I said, that here observables correspond to self-adjoint element of algebra. Please scroll. So as I said, as already in the very beginning of quantum mechanics, was realized that it is better to consider only the state of self-adjoint element. It is closed with respect to operation of anti-commutator. Usually this anti-commutator is divided by 2, but this is not quite necessary. And the Jordon algebra is an axiomatization of this operation. And this is the natural framework of algebraic approach. What is Jordon algebra? You should consider a commutative algebra, which I assume that it has a unit. It is a unit of algebra. And I define an operator Ra, which is an operator of multiplication by A in this commutative algebra. And the Jordon axiom is that the operator of multiplication by A squared should commute. This is the standard definition of Jordon algebra. And what I would like to stress, that this is really a very natural notion, because you have the following theorem, that the cons of states of 2 C-star algebras, and usually don't want to give the definition of C-star algebra, it's not important for me. But the con of this is the class of algebras that usually are used in all this business. And you can consider cone of states in C-star algebra. And they're isomorphic if corresponding Jordon algebras are isomorphic. So that we will consider only this cones of states. And so this is means that for us, Jordon algebras are very natural. Please scroll. But what I would like to say now, there exists another axiomatization that leads to a little bit different notion of Jordan algebra. So with Jordon considered the operation of anti-commutator because it axiomatized it. He took this anti-commutator because the set of self-adjoint elements is closed with respect to anti-commutator. But there is another operation that has the same property. This you can consider operators Q, A, that transform X to AX, A, where A is self-adjoint. And again, this operator acts on self-adjoint elements. And you can try to axiomatize this notion. And this was done much later. And it was defined, this led to the notion of quadratic Jordan algebra, which is with appropriate state of axioms is equivalent to the notion defined by Jordon. And this is really more natural in my setting, but I will not use it. And I will say only one thing, namely that in Jordan approach, you can express this operator QA by the formula which is written right here in terms of operator multiplication by A denoted by RA. What I will do, I will consider, sure, I will work in Jordan definition, but the operators QA will play a very important role in my business. And also I would like to notice that operator QA is quadratic with respect to A. So it is a very quadratic function. It can be extended to symmetric bilinear function, and then it is denoted by Q A tilde A. Please scroll. Now, what I consider Jordan algebra denoted by curly beam. So when I consider Jordan algebras, I will always consider topological Jordan algebras, which means that they have some topology that the operations are continuous in this topology. But usually it's sufficient to consider what is called Jordan-Banach algebras. I will not define them, but it's Jordan algebras with dark Banach spaces. You should you can think about the Jordan-Banach algebra. And I would like to define a cone in such an algebra as the smallest convex closed set, which is invariant with respect to the separator QA and contains a unit element. This is not a standard definition of a cone in Jordan algebras. Usually people consider only Jordan-Banach algebras defining the cone. And they are saying that they are saying that the cone of positive elements is the cone of all squares of all elements of the form A squared. But for Jordon-Banach algebras, these two definitions are equivalent. But in general, you can say that QA applying to unit element is precisely A squared. So the cone in my definition contains of all squares, contains all squares, but it can contain also other elements. So I have a notion of cone of positive elements in any Jordan algebra. And I can consider also the dual cone. It consists of linear functionals on B that are non-negative of the cone of positive elements. So in my geometric approach, I can construct a quantum theory starting with more or less any cone. So I can construct a quantum theory starting either with cone of positive elements in Jordan algebra, or starting with dual cone. And I can relate it to definitions of algebraic approach based on star algebra. If you are starting, if B consists of self-adjoint elements of C star algebra, then the elements of dual cone can be identified with positive linear functionals on star algebra that are denoted, that are defined as states in algebraic approach. So what do we get? We see that if you have a Jordan algebra, then you can construct a quantum theory, and this generalizes algebraic approach that is based on the star algebras. So now I should say what does it mean to consider evolution operators in this case. I should define the group V, and I will define the group V as a group that is generated by invertible operators Q A and automorphisms of B. And this definition leads to is equivalent to the standard definition of structure group of Jordan algebra. Please scroll. And then I can define, if I have a Jordan algebra, I can define everything that I can define in general geometric approach picture. In particular, I can define particles and scattering of particles. So I will give these definitions starting this general theory. So what I need to give this definition, I need really the cone of states, of non-normalized states. It is more convenient for me to work with non-normalized states in this setting. And so I need this group V that I'm using to define evolution operators. So I need time translation that should be identified with evolution operator. And I need also spatial translation. So altogether, spatial translation should form a commutative group. So I can say that I have a homomorphism of commutative group of translation into the group V. So that's this will be sufficient for me to define particles and scattering. But if I would like to have a relativistic theory, I should extend this homomorphism, these translations, to Poincare group. I should have a homomorphism of Poincare group to this group V. And after that, I can define quasi-particles that are elementary excitations of translation invariant stationary state, denoted by omega. And particles are simply elementary excitation of ground state. So if get this definition, but I did not define the notion of elementary excitation, so that the elementary excitation will be defined to the next slide. Please scroll. To go to the notion of elementary excitation, I will come back to algebraic approach. And I would like to remind that having a state omega, a positive function on the algebra, I can construct a representation of star algebra A in some Hilbert space or pre-Hilbert space, I prefer, that contains a cyclic vector theta, such that omega of A is the inner product of theta and A theta. This is called Gelfand-Naimark-Siegel construction. And it is always used in the algebraic approach. And this means that really every state that I have said that every state can be considered a state in Hilbert space. But different states omega, they give different Hilbert spaces, so we have infinite number of degrees of freedom. So physicists usually do not use this notion of Gelfand-Naimark-Siegel construction. They're simply saying that, okay, if you have an algebra that we consider a Hilbert space when this algebra is acting, and then you can consider for every element, you can consider some state. So this, we are using this formula without saying the word Gelfand-Naimark-Siegel construction. But I would like to use this word, and I would like to stress something that, again, physicists considers as something completely evident, but this is really very simple mathematical fact, that if you have translation invariant state, translation invariant with respect to spatial translation and with respect to time translation, then the action of translations descends to this Hilbert space that you are considering. And after that, you can consider operators of infinitesimal translations. It gives you momentum operator and Hamiltonian energy operator, which is denoted by P and by H. And after that, you can say that if you have a particle, then you should have a notion of particle having some momentum denoted by small p, and you should, this notion of particle with given momentum gives a vector phi of p that should be really an eigenvector both of momentum with eigenvalue p and energy operator with eigenvalue epsilon of p, where epsilon of p is what is called this function is called dispersion law, and this is relativistic case. This is square root of p squared plus m squared. But for me, this is irrelevant. I can consider non-relativistic picture as well. So this is standard definition of notion of particle. But I would like to say this in a little bit different words. Namely, I would like to say, first of all, that phi of p is really not a vector of Hilbert space. This is a non-normalized state. And you should consider really integrals of phi of p, all phi of p by capital phi of p dp, which is written here. And you will have really a good vector only after integration. So this means that you have the particle is a generalized function with values in Hilbert space. So you have some space of test functions, and the particle gives you a map of test functions into Hilbert space. And you have a natural definition of spatial and time translation in this set of test functions. So if you are here, I have these test functions in momentum representation, but I can work in coordinate representation. Then you have simply translations in coordinate space that gives you spatial translation of test functions in momentum spaces definition of e to the I p a, where a is the vector, subvector. To define time translation, you should have in mind that they should commute these spatial translations, and this defines uniquely, almost uniquely, time translations as multiplication by exponent where you have tau multiplied by some function epsilon of p in the exponent. So for reasonable definition of time and spatial translation test function, you will see that this particle, it defines a map of test functions to the Hilbert space, and this map commutes with translation. So instead of this formal definition of a particle, I can define an elementary excitation as a map of test functions to Hilbert space that commutes with translation.
Mhm.
And this is the definition that I will generalize in geometric approach on the next slide. Please scroll. So, in geometric approach, my states are elements of the cone. So really, when I go from Hilbert space to the cone of states, so they use the standard formulas. So every element of Hilbert space defines a state. Density metrics in quantum mechanics, or it defines a positive linear function on algebra approach. So I say that a map, that elementary excitation is a map of the space of test function into the cone. And again, I would require that this map commutes with translation. I could say that this is the definition of elementary excitation. But this is not, it is sufficient for developing the theory. And I would like to say that in algebraic approach, every element of my Hilbert space, and by say 3 Hilbert space, can be obtained from the vector theta corresponding to omega by means of action of element of the algebra. This is definition of metricity. So it is natural to assume that this element of the algebra is linear with respect to test function. But when I go to the cone, when I consider states in as elements of the cone, positive function of the algebraic approach, then I get a quadratic expression instead of linear expression. So really, this is it is not really quite really quadratic. It is sesquilinear. It is, but I will use the word quadratic, which is not quite correct. But I hope that you will forgive me. So I'm requiring that this map, this elementary excitation, is a map of test function to the code. It is not linear map. It should be a quadratic map. And it should be represented in the form sigma of phi is equal to L of phi applied to omega. It should be a kind of excitation of omega. Should be obtained from omega by means of some operation that I denote by L of phi. And to define scattering, I need some kind of asymptotic commutativity. I do not want to define formally by many reasons. One of them is to take some time, and I think that I do not have enough time for giving the precise definition. Maybe it seems that I do not have a lot of time remaining. But I will require that the following property, that if supports of phi and phi prime in coordinate representations are far away, then L of phi and L of phi prime should almost commute. The commutator of them should be small. So, and I have said that this L of phi is considered as quadratic, better to say, sesquilinear map, and this means that it should be obtained from bilinear map, or better to say, that is not bilinear, it's linear with respect to one argument and a linear with respect to another. Please scroll. So I don't think that I have enough time to explain in detail the involution of scattering matrix, of inclusive scattering matrix. I will say that later in a moment. But I introduce some operators here on the first line, second line. And starting with these operators, I consider some expression which is defined by taking limits when time go to minus infinity. Then I will get this last line here is the definition of scattering state. And then I consider some stuff that can be defined in terms of the scattering state. And they take limits when times go to plus infinity. And the theorem is that imposing some conditions, I can prove a theorem that this this expression has a limit. And of course, I cannot give any proof of this theorem. But it's not very complicated. I can give only some ideas in 1 minute. So look, what here I can start with a definition, with application of some operator defined in the first lines to omega. And this definition of operator L is given in such a way that this, applying this L to omega, I will get expression that doesn't depend on time. This is easy to prove from my requirement. But after that, all of my L that are written here for dense set of argument, they almost commute. And therefore, I can really permute this, all of these factors to the rightmost place to give independence of time. Sorry, I understand that I'm not saying something that can be explained in 1 minute, but so really imposing this condition of almost commutativity, I can prove the existence of limit of scattering method. And this is a far-reaching generalization of what is called Hague-Ruel scattering theory in algebraic approach. Please scroll later. So there is one thing that I should wanted to say. I said the word inclusive scattering matrix. I defined this notion on the previous slide. However, I did not explain why I'm calling this inclusive scattering matrix. This is because inclusive cross-sections can be defined in terms of inclusive scattering matrix as in very simple way. And then inclusive cross-sections, it's sum of cross-sections when I'm looking only on sums, products of reaction, and discarding other products. So this was a formal definition of inclusive scattering matrix. And there is the most important question that a physicist should ask, how to calculate this stuff. And the answer is that they can be expressed in terms of generalized green functions that appear in Schwinger-Keldysh formalism of non-equilibrium statistical physics. I have the time to explain this, but I can answer if you have to ask me questions later, but I can explain this, what does it mean. Next slide. So what, as I said, in the framework of Jordon algebra, it's quadratic stuff that appears very naturally. This is this operator QA is quadratic, and this operator QA acts in the cone. So, and therefore, you can start with linear map of test functions to Jordon algebra. And then you can define elementary excitation, taking Q, this argument rho of phi, and then you will get an elementary excitation of the stationary of translation invariant stationary state in the dual cone. It is more convenient to work with dual cone here. And you should impose the condition that this Q of rho of phi almost commutes with Q of rho of phi prime when phi and phi prime have this distance support in coordinate representation. So please go to the next slide. And then there is a question how to see when this operator Q almost commute. And really, it is can be proven that if Jordon product of two elements of Jordan-Banach algebra is small, then corresponding operators Q almost commute. And the formal statement is written here. So this gives possibility to define fermions in Jordon algebra setting. Mm-hmm. I do not want to talk about the definition of bosons, but the main statement is that if you have Jordon algebra, then all the definitions of geometric approach have a very simple interpretation. Mm-hmm. Please scroll to, I believe, to the last slide. So, and now there is a really important question that I did not solve, and I think that it is a basic thing that is absolutely doable, is to construct an interesting examples of all the stuff in the case when you have exceptional Jordon algebra. First of all, let me say that if Jordon algebras come from algebraic approach, then there is no question. There is a lot of every example of integral theory coming from algebraic approach can be formulated in Jordon algebra approach in a very simple way. So there is no question of examples, constructive examples from Jordon algebra. But there is a question of examples that are not covered by standard algebraic approach. And then you should work with what's called exceptional Jordon algebra. that can be realized, that cannot be realized in setting of associative algebras. And this exception, there is only one exception, Jordon algebra, which is simple. And it's called Albert algebra. It is an algebra of 3 by 3 Hermitian octonian matrices. It is simple, but you can construct many other algebras that are not simple. I don't have any assumption of simplicity in my simplicity in my setting. So I should consider Albert algebra multiplied by some commutative ring. Or this is the same. I should consider octonian matrices with entries from this commutative ring. And then it is very easy to construct Poincare invariant Jordon, to construct Jordon algebra this action of Poincare group, because the structure group of Jordon algebra it contains the group SO19, Lorentz group of 10 dimensions. But this is, but the translations cannot be defined in algebra, in Albert algebra in good way. But if you multiply it by commutative ring, then there is no problem. You can consider representation of Poincare algebra in this commutative ring, and you'll get an action of 10-dimensional Poincare group on Jordon algebra. And I hope that this way you can get physically interesting examples. But to do this, you should construct interesting Poincare invariant state and interesting elementary excitation. And this is the problem that I need to solve. I think that it is a very interesting problem. And the last thing that I should say, that really what I talked about Jordon algebra, but really I can take a Jordon superalgebra and Jordon superalgebras which are equipped with ratio, which should be identified by physics as PRST iterator. And you can construct this stuff taking this R differential supercommutative ring, for example, a ring that is used where you calculate homology, cohomology of super the algebra. But I don't think that I have time to talk about this stuff. So please scroll to the next slide. Sorry, this is already a slide about something else that I hope to have time to explain, but I do not have this time. But I can answer your questions if you would like. This is something that I mentioned from the very beginning. Namely, I said that if you can, in classical theory, can see only a part of observables, then you can obtain a lot of interesting series. In particular, you can obtain usual quantum mechanics. So this is the end of the first hour. I think that I was a little bit late, but hopefully this is okay. So now I can answer your questions. And,
Okay, so should I open it up for questions, Albert?
Yeah.
So, yeah, thank you very much for a really beautiful talk. There's a question. One minute. So should I stop sharing the slides or continue to share them? What would you prefer?
Probably, I believe the next question is the question is for about slide 15. So probably
okay. Let's see if I can open that. Where I have to go to the chat, no? Yeah, okay, I'll read the question from David Chester. On slide 15, are the momenta R1 to Rm? Okay, maybe I go to slide 15 first. Okay, here's slide 15. On slide 15, are the momenta R1?
Oh, the slide 15. Oh, slide 15, yeah. Okay, yeah.
Are the momenta R1 to Rm also taken to be on shell? Are the Ri? So I'll just complete the question. Are the Ri taken as final momenta, or do they represent intermediate virtual particles?
No. This here, everything here is on shell. No intermediate particles. In all the theory, there are no intermediate particles. Everything, what does it mean? So really, when you consider the generalized green function, then of course you can consider them on shell. However, when you consider they can be off shell with green function. But when you go to inclusive scattering matrix, you should consider green functions, generalized green functions on shell. So the momenta in this inclusive cross sections, all of them are on shell.
Thanks for the talk. So are these inclusive cross sections for specifying processes where you specify some final particles Q1 through Qn, but then you're allowing for the possibility of other unknown particles to come in and summing over all of those? Is that the idea?
Yeah. This is the standard definition of inclusive cross section. So that's it is not covered in standard textbooks, so therefore I wanted to give the definition, but this is standard.
So as I said, the talk is open for further questions. Kindly use the raise hand feature, and then we can proceed. Yeah, I think Cole, go ahead, please. Go ahead, please.
Okay, yeah, thank you very much for your talk. So I wanted to ask very early on, you were describing a Hamiltonian as being an element in a Lie algebra that was describing the automorphisms of your space of states. And it seemed to me like there was probably quite a bit of freedom in what the Hamiltonian could be, if that's where it's coming from. So I was wondering if perhaps it's something that you said, and I missed it, but do you have a way of singling out what the Hamiltonian should be in your formalism?
So let me say the following thing. First of all, there are two questions here. So in my business, it's Hamiltonian, or better to say Hamiltonian quotation marks, because this is not a standard Hamiltonian, standard quantum mechanics. It would be action density matrices given by commutator with Hamiltonian. So this is you can the answer is the same as in usual quantum mechanics. In usual quantum mechanics, you can take any self-adjoint operator as a Hamiltonian. Anyone. But there is another question. So in my case, in my situation, the answer is the same. You can take as Hamiltonian, I have this Lie algebra, this Lie group V that contains all evolution operators.
Mhm.
And you have Lie algebra of this group. And every element of the algebra of this group can be considered Hamiltonian, in quotation marks. There is another question.
So they're all equivalent. All the traces are equivalent, you're saying?
Sorry?
They're all equivalent, you're saying?
I think Cole is saying that according to you, they are equivalent.
Sorry, I didn't get.
Could you try to repeat, Cole?
Yeah.
So you're saying that they're equivalent. That's equivalent.
So let me say this same stuff for quantum mechanics. In quantum mechanics, you can take any self-adjoint operator as a Hamiltonian. But there are most operators are not interesting for physics. And there is a question how to construct interesting Hamiltonians. And the same problem is you have in my formulation. You can take any element of the algebra of the group V as a Hamiltonian. But there is a question, what is interesting?
Right.
Did I answer your question?
Well, actually, I do have another question. In principle, if you were to choose very carefully your set of states in the right way to say have something that corresponds to the standard model, and if you were to choose your Jordon algebra properly, could you in principle be able to reproduce any of the scattering amplitudes from the standard model using your framework?
So really, the theory that I'm developing is really a generalization of standard quantum theory. So that's what I have here. So basically, I have some very simple axioms that can be really used to get everything that you have in quantum mechanics. You can, as I said, you can prove the coherence, and I prepared some slides to explain how to prove the coherence in my setting. The coherence leads to the expressions for probabilities. I did talk about stuff. I talked about definition of scattering matrix. This is a general theory. If I can, of course, I can take the standard model. The standard model can be formulated in the framework of, say, of algebraic approach to quantum theory. You can consider that you have fields there. They generate some algebra. You have an involution, which is simply Hermitian conjugation. And you have some action of time translation, spatial translation. You have everything there. So therefore, the standard model definitely, every physical theory that can be formulated in terms of standard quantum mechanics can be formulated in my approach. Of course, this is the meaning of your generalization.
Mhm.
Question is, what else can you do? What I'm trying to say, that there are interesting models that are in my approach, but cannot be covered by standard quantum mechanics. They can be formulated. You can consider corresponding physics, but this is not. This goes beyond quantum mechanics, and so that the slides that I wanted to show, but didn't have time to show, they are about the stuff. Like probably it is reasonable to show them.
Would you like to use this time to show the remaining slides?
Yeah, I would like to do this.
Let's do that. I try to go to your slides. I'm just looking for them. Yeah, it's here. Okay, so we had done slide 19. We had done, yeah.
Yeah, that go to the next slide 19. Please show it to me.
This one, this one.
Yeah, this one.
Okay, please go ahead.
Okay. So what? Could you show the previous slide? This yes, this is it. This is so. What? This is the statement that I would like to explain, and I think that it is really important. So what I'm doing, I'm taking some Lie group G, capital G. I'm taking its Lie algebra. Then I'm taking a dual space G. In this dual space, in G, you have a joint representation. In dual space, you have what's called co-joint representation, a co-joint action of the group. And you can consider orbits of this action, which are well known in mathematics and in physics. There is what is called orbits methods in representation theory. Quantization of these orbits leads to unitary representations. So but I do not need this. I take an orbit of co-joint action, and it is well known that this orbit is a symplectic manifold. You can consider it a phase space of classical system. But then, what can you say is the elements of Lie algebra G, they specify functions on G dual. That's really elements of G. So this means that G is an element of double dual to G. So we have element of G specifies a function in G dual. And therefore, you have some function on n. This function is n, the Poisson brackets of them is governed by the algebra G. This again is well-known stuff. And then what I'm saying, if you consider this manifold M as phase space of classical system, and you are saying that only these elements of G can be observed, can be measured by our devices, the statement that I would like to make, that then the classical theory is equivalent to a theory when the space of states is a convex envelope of n. So basically, this, if you think that, if you allow possibility that not everything can be measured, then you will get a theory that can be described in geometric approach by means of some convex set, which is convex envelope. Then the next remark, that you can take Sm projective space. Everything here can be told about infinite dimensional symplectic manifold. You can take infinite dimensional projective space. And then the statement is, then you get a conventional quantum mechanics. The conventional quantum mechanics is a classical theory on projective space, where you look only at part of observables. This is the first question that I wanted to say. The second thing that I would like to do, please go to the next slide, that you really can prove this very easily. So this one-line proof, which will be which is explained on the next slide. And on this slide, I have only the explanation. What is this? What is this? What are the conditions? So you have really, again, I consider more general case. M is any symplectic manifold. And I assume that I have some set of observables, the functions that can be measured. And I assume that the set of observables is closed with a linear space. This is closed with respect to Poisson bracket. Then I can talk about this, can say that this set is the algebra, they do not by G. And then I can say that these elements can be considered as Hamiltonians. That generates some Hamiltonian vector fields. These functions are denoted by a small g, that corresponding Hamiltonian vector fields are denoted by a capital gamma, a gamma here and here. So that's this is my setting. And then I go to the next slide. Then I can define a moment map of M to G dual. So it's, this again is standard definition. And this is definition is very simple. So really remember that I had functions A with index gamma of X. Gamma was from the algebra, X was from N. Now I interchange this function of two variables, but I consider gamma as a parameter, X as a variable. Now I go in opposite direction. I consider X as a parameter and gamma as a variable. And then I will get a linear function of gamma. My A gamma are linear with respect to gamma. So I get a map of M to G dual. Here I have linear because I have linear function of gamma here. So this is the standard definition of moment map. And now, what can I say? I can say that for every state of classical system, the state of classical system is a probability distribution on M. I can define some point of dual space to G as an integral, which is written here. And this is the map of classical states to points of convex envelope of mu of M. Next slide, please. And after that, there is a very simple proof of the following statement. That if we say that two states are equivalent, we say that two states are equivalent if they give the same result for every Hamiltonian A gamma. And this is the proof of the theorem, that two states are equivalent. They give the same result for my set of that I singled out. If they give the same point in the convex envelope of the image of M. And the proof is here. So it is not necessary to explain anything here. If this in the right-hand side, I have the result of calculation of my Hamiltonians, of my observable. And I see that these results are equal if corresponding points in some convex set coincide. In particular, you can apply this to projective space, and you will obtain the statement that I made for classical, usual quantum mechanics. If you take projective space, then your envelope will consist of density matrices, and you will see that you will get quantum mechanics from classical mechanics if you get if you are able to measure only observable observables. But if you take something else, you get something that goes beyond quantum mechanics. But still you can apply all the theorems that I proved. And so that's really what do I have, what I try to explain now is that there are many interesting models that go beyond quantum mechanics and still can describe something.
Should I stop sharing, Albert, or you want to go ahead?
So let's say
Next slide.
that's the end. That's the end of this story.
Okay.
As another stuff is that I
Yeah,
want
it's a-
to explain is how to get the coherence.
Do you think we should come back to the discussion?
So yeah.
Yeah, because just want to see if people have more questions. Yeah, thank you. Thank you for this part. So actually, I would like to ask you something. You know,
Yeah.
if we recall the 1934 paper by von Neumann, Wigner, and Jordon, where they looked at the classification of the Jordon algebras,
Yeah.
they conclude that there is the Jordon formulation would give the same say experimental results as the conventional formulation of quantum mechanics, except for the case of the Albert algebra. So I'm curious, do you agree with them on this?
So if you have yes, it's in a sense that if you do not consider this Albert algebra, then Jordan algebras can be used, and maybe they are useful, but they do not go outside of standard algebraic formulation. What I'm trying to say that if you have, but still, if you have Jordan algebra, this Albert algebra multiplied by some commutative ring,
Mm-hmm.
then there is a chance to go outside. But
So let me ask. So what are your thoughts, maybe, about what is the significance of the Albert algebra, say, for particle physics? Do you have some thoughts on that?
so that's what is okay. There are many attempts to apply this Albert algebra to particle physics, and these attempts, I think that it is. I think that it is clear from this the results that are here that Albert algebra should play some role. That's definitely true. So basically, the very fact that that structure group of Albert's algebra contains SO19 is very suggestive. It seems that it should be important for superstring. It should be important for. Yes, that's. I agree with this. The only problem is that neither I nor the people that wrote papers about the stuff, this is only an indication I would not say that it's proven. I said that there is an indication that Albert algebra is a problem.
Yeah, also keeping in mind, for instance, that the Albert algebra consists of 3 by 3 Hermitian matrices, and also that there are 3 fermion generations. Maybe there is some connection between the three number that appears in both the circumstances, for instance.
Yeah, I think that this is ideology of Dubois, Violette, and Todorov also works in this direction. So this is a very interesting conjecture. It is, I do not think that they proved this, that there is such a relation, but definitely they have some very important indication that this is possible.
Yeah, and also a couple of other remarks that, you know, the automorphism group of the Albert algebra, I think it's E6, which is also the symmetry group of the Dirac equation in 10 space-time dimensions. Again, very suggestive to, you know, you're bringing in SO19.
There is one more indication that this is true. There is what is called pure spinor theory. Pure spinor theory, they are related to what is called Jordon pair, which is defined on the direct sum of 2 octodian algebras. It's also an indication that something is there. But okay, this is only an indication.
Yeah, also one last remark, you know, around 1999 or 2000, Tavian Dre and Corinne Minogue, they studied the characteristic equation of the Albert algebra, which is a cubic. It's a very simple cubic like would arise in ordinary 3 by 3 matrices. So, I mean, I wondered what is this characteristic equation, what are its eigenvalues telling us about elementary particles? But if there's something new in the Albert algebra, it has to be in this equation.
I don't know. In some sense, I believe this equation is something generating sort of light cone equation, yeah?
Yes, yes.
And yeah, maybe probably it is possible, I don't know if it is true, that convex envelope of the solutions of this equation is precisely this convex cone that I consider. I'm not sure. I do not know, but this is a reasonable question to ask, and probably people know the answer. But I don't know.
Thank you. I think David has a remark. David, could you please discuss your remark?
Yeah, for sure. As Albert was mentioning, the octonian's relationship to d equals 9 plus 1 is curious. And so one thing that I noticed hasn't been explored yet is developing an octonionic spinor helicity formalism. So I mean, this isn't even really exactly a question. I just figured I would mention it and maybe ask if you've thought about this at all. So for instance, typically you can have complex spinors as 2-component spinors. You could generalize that to octonions and then consider inner products of octonionic spinors to get arbitrary scattering amplitudes in d equals 9 plus 1. And then BCFW recursion would allow for you to recursively find arbitrary endpoint scattering amplitudes for classical tree diagrams from the 3-point scattering amplitudes. So I just figured I'd mention that.
I do not know this result that you have mentioned. Probably this is, I think that what I can say that really you can formulate this what is called the FSS matrix model in terms of octonions.
Mhm,
It's possible.
mhm.
So I did this at some moment with Bubsi Kim, and I even wrote a note that never published, but still it referenced in some papers by Smolin. But anyway, so this is yeah, there is a relation, and I would like to, if I would like to ask to send to me some references in this
Mhm,
to these three amplitudes in terms of octonions that
mhm.
would like to know.
Right. So I guess my comment is that it's been done with complex numbers, but not yet with octonions.
Mhm.
So most people are interested in D equals 3 + 1 physics typically. I mean, besides string theory. So, but there is an opportunity to try to generalize complex spinors to octonionic spinors and explore that. It
Yeah.
shouldn't be too difficult. The main issue is that the helicity state, the on-shell, I mean, the massless little group in D equals 9 + 1 is now spin 8 instead of spin 2. And so that becomes non-abelian. So when we're in extra dimensions, a non-trivial point is that the solutions to the fields have different helicity states, and those helicity states can be assigned an index in relation to the little group index. So the fields and the solutions to the fields actually have different tensor structures, you could say. And so that is one thing to consider when going to octonionic spinors, is that the solutions to the fields, there would be more solutions than the fields themselves, so that the index structure is a little different. But
Yeah.
yeah, I could try to find some references that might be relevant.
Thank you.
Yeah, thank you, David. Well, one more point, Albert, that the modern developments related to using octonions in particle physics is that spinors that describe fermions are naturally made from complex octonions, not from complex numbers. This is perhaps, seems to me, is one thing that was missed out in string theory, even though they had the E8 cross E8 heteroctic string, they had 10 space-time dimensions, S1 or SO19. Particle states are always being defined using complex numbers, and the octonions don't make a fundamental appearance. This seems to be one place where string theory has missed out. And do you have thoughts on this, or do you think I'm saying something wrong?
So I don't know. So really, so as I said, that I believe that octonions, or exceptional Jordon algebras, they should be important for superstring. I strongly believe that this is true. But this is only I believe, and I think that there are many connections. Still, there is no convincing evidence.
Yeah. For example, if the E8 cross E8 heterotic string theory is anomaly free in 10 space-time dimensions, that certainly has something to do with the octonions and with the Albert algebra, but it's probably not clear what that is, isn't it?
No, so there is one thing that is already well known. It is that fierce identities that are necessary for from supersymmetry. They can be proved only for division algebras. And this is, means that in particular, Cartonians do appear in this business, in business of supersymmetry.
Yeah.
But
Then, yeah. What is the reason that string theory does not pick a unique standard model? What is the reason for that? I mean, I understand that compactifications are non-unique, but there must be a more fundamental difficulty, you know, something that we are missing.
Maybe, but I would like to say one thing. First of all, string theory is not necessarily correct. And the sense, this another remark, it's a funny remark. So really, I thought that really this landscape situation when you have many possible ground states is not satisfactory. However, later I realized that this is not necessarily true. And the comparison is for basically imagine that you have some very intelligent small insect, say ant, something that lives, not necessarily insects, but that lives something deep in the ocean, and then it shows that in his physics is a physics of medium that can be described as we say this he lives in water, but this is his world. But he really invents some physics, and then he realizes that in his physics, his surrounding, his ocean, is only one possibility. That there are many other possibilities. And what? So really, maybe we are this small animals living in some ground state. We discover there are other ground states, but there is no preference to our ground state.
So suppose that is true, but I would have thought even in that case, I should be able to, for example, prove that the muon is 200 times heavier than the electron in my universe. Why am I not able to do that?
I don't know, but so I definitely know that the speed of light is less than my medium. Yeah, the speed of light in water is not the same as. So that's so basically the same as again situations. Nuance is also not so clear because basically even electron is really covered by a cloud of photons. The same is true for any particle, not only in water.
Yeah, but but one would still say there is no theorem which says that the fundamental constants of the standard model cannot be derived and string theory is the final word. We don't know, right?
We don't know, but I hope this is not the case. I hope that we can derive everything fundamental from some general theory, but this is not necessarily true.
Thank you. Thank you. That was a very interesting discussion. So if there are any more questions, kindly go ahead. David, you have another remark. Why don't you say, talk about it?
Oh, I was just mentioning the relationship between octonions and E8 is fairly well understood. However, it's only been very recently that people have understood how to implement E8 Lie algebra transformations with octonions, particularly using a tensor product of octonions with octonions by Wilson, Dre, and Minogue. So that kind of provides light on why string theorists wouldn't have been able to do this, say in the 1980s and 1990s. There's been a lot of progress with mathematics of octonions in the past few years. And so, yeah, now's a good opportunity for progress.
So do you think string theorists should be looking at this progress? It has value for them?
Yeah, it definitely can. It definitely can. But I mean, a big part of the problem is that a lot of people seem to have realized that octonions might have been useful in the 70s, but now most people move on. But I mean, people like Mia Hughes and Michael Duff have been exploring octonions in supergravity. And so it's now understood that all of the supergravities are classified by division algebras. So it's really inevitable, that all the division algebras relate to the dimensions of spacetime with supersymmetry that they utilize. So yeah, all of this will become relevant.
Yeah. So Albert, I want to read out this remark from Greg Trailing, which you can see in the chat. String theory has not yielded a single parameter in the standard model. I sympathize with that. For me, honestly, that means string theory is a failure, at least in this regard. I agree with Greg on that.
String theory is definitely not a failure, because it's led to very interesting mathematics. It's led to very interesting conjectures. Maybe it is not clear that it is connected to physics. But when I'm saying talking about string theory, I always saying that string theory is not necessarily correct, but really the correct theory will be built on string theory.
I agree. No, I meant failure as a theory of unification. Only in that context. And yeah, I think in my view, the Albert algebra needs much closer attention. It is, the forgotten part of the Jordon algebra. I think because the rest of the Jordon algebras are equivalent to conventional quantum mechanics, the Albert algebra was forgotten, but maybe that was a mistake. Yeah. So anything more, or you like to? We are almost at the end of time, so I think we had a wonderful talk, Albert. Thanks so much. And next week we move more thickly into the octonions. Niels Gresnick, 2 weeks from now, April 7, will talk on Cayley-Dickson algebras and their applications to particle physics and the standard model. So if there are no more questions, I'll say bye to all of you and see you on April 7th. Thank you.
So,
thanks for the talk.
So thank you for listening. So goodbye.
Bye-bye.